Hello there, Mr. Griffin. How you doing?
Hello, Taylor. I'm doing okay.
Good. Hey, I wanted to let you know I started a new job recently where I'm a pandemic pod tutor. So I have a couple of kids I look after here while they do their schoolwork. And so that's why I'm not able to respond to you whenever you call on me during class.
Oh, thanks for telling me that, Taylor.
No
I'm
problem. I record the screen so I don't have to wait till the weekend to watch it and I can just watch it later in the day. So I'm
Yeah,
recording on my
that's
computer.
beautiful. Good.
Okay.
I'm glad you told me because otherwise I'd think you didn't care.
I certainly do. And I feel so bad hearing you call on me and I'm like, oh no, I'm not there.
But thanks.
Mhm.
I'll still
I also
might
had a
try to call
question.
on you sometime. Maybe I can catch you when you are there. But
If so, I'll definitely jump in, but I don't want you to think I'm ignoring you.
yeah, uh, I'll try to remember that, Taylor, but I wouldn't hold it against you in any case, because I
I
understand
appreciate that.
students have all kinds of other responsibilities.
Right.
Well, let's see
I had
here.
another question too, actually, about the YouTube page.
Yeah,
Have you heard that there's a couple of videos on there that didn't get uploaded or were deleted?
uh, I haven't heard that, but my IT person worked on it last night, and check again. Uh,
Okay. Yeah, I haven't checked it since last night. I'll go check it
yeah,
right
you
now.
check again. She's pretty darn good. Let's see.
All right. Yes.
It's just you and me, Taylor. We're nobody else has
Looks
showed up.
like it.
There's the scores on the exam, and
Looks pretty good overall.
I posted those, and let's see. You got. I wonder if I can tell you this without. Probably shouldn't. There might be
Somebody else
somebody
is
else,
here.
but you can look it up. You did pretty good.
Okay, I'll go ahead and look it up.
Yeah, you did all right. And
Glad to hear it.
let's put it this way, Taylor. You were right in here. See that? Well, wait a minute. That
Yeah.
I think I think I just told the world. Oh well.
I don't
That's
think
just
anybody else saw. It's fine.
yeah, yeah. You're in there. Yeah.
Well, that's good. I'll take it. It
You
was
did.
a pretty busy weekend. I was working on that, and my brother's getting married next weekend, so I was planning a bachelor party for him at the same time, and
Yeah.
just took care of that last night. So I was rushing all weekend.
Older or younger brother?
Younger brother,
Younger brother. How old is
he's
he?
about 5 years younger than me. He's about 26,
Oh, well,
26, 27.
you're an old guy.
I'm an old guy. You can't tell
Yeah.
because of the mask, but I'm 31.
Yeah, you're you're over the hill, man. Don't trust anybody over
Taking,
30.
I don't. That's why I stopped trusting myself.
Uh, let's see. We still have 3 minutes before class, and we've had some laughs already. That's good. Yeah.
Yeah. All right. Looking up that.
Ashley is with us. Yay, Ashley. We got three of us so far.
I appreciate you getting this test graded so quickly.
Yeah, and I have another. See, I have three classes, so I have a humongous pile of work to do today.
I would imagine.
But that will keep me out of trouble. I won't have any time to get into trouble. But the sad thing is,
That's true.
I won't have time to do honeydew jobs for my wife.
Oh no, that might
Yeah,
get you into trouble.
yeah. There's different kinds of trouble.
Exactly. Got to prioritize which ones you're willing to be in.
Yeah.
Mhm.
Ah,
How's your weekend?
well, let's see. Trying to remember. I went to a grandchildren's play at their school.
Oh,
Took
how
the
fun.
dog. Took the dog for a walk. Stayed sober all weekend. Uh,
Impressive.
impressive.
Can't say the same.
Impressive.
Mhm.
I don't remember what else I did, but I enjoy my weekends.
That's good.
Well, how about any of my other students? Do you have, Ryan is with us. Yay, Ryan. Any of you have any questions for me? Anybody? Because we're going to start here. We're going to talk about work energy today. Your homework is homework number 26, fundamental problem 18.4 on page 488. Well, let's start with a little theory, I guess. Stuart's with us. Yay, good going, Stuart. Glad you're here. Here's your last chance. Anybody wants to say anything, because I'm going to start talking about the work energy theorem here. We're going to talk about work energy theorem. Well, let's talk about work first. Nobody's saying anything. This is the results of your exam. They are posted on Blackboard. And I'm going to erase all that here in a little bit because I need the space. But work, there's two different kinds. There's this kind here, and there's this kind here. And you'll see these in your chapter. See, this is linear or translational work, and I know you've seen that before, but this is rotational work. That might be a little bit new to you, I don't know. It's on page 478. See, this here is it's a bending, not a bending moment, it's a moment of a force, which is in Newton meters. And the differential amount of radian change, or angular change, that's dimensionless. So the dimensions for work with this equation are Newton meters, which of course is a joule. And we all know that that's the unit of work. Now on this one here, see what that is newtons times meters, because distance is measured in meters. So you get Newton meters, which of course is a joule. Ta-da! So there's your two equations for work, and you'll find that first equation on page 476. This one's on page 476. Yeah, to be absolutely correct about it, it's a dot product of two vectors. But if they're going in the same direction, you don't need the dot product. In fact, if you take the tangential component that's along the path, they will be in the same direction, and you won't need you don't need to worry about a dot product. Well, there's your definition of work. Now let's write the work energy theorem. Any questions so far? Okay. We're having a little teeny tiny bit of theory here for a minute. Here's the results of your exam that you guys took. The class average was 82. So it's just kind of right in the middle there. 82 is kind of in the middle, isn't it? So the class did pretty darn good. I didn't have to curve it. See, when the average is 82, I don't curve it. Well, let's see who's on board now. We've got, oh, we got a good crowd. Jesus, Mark, Braxton, Ashley, William, Taylor, Stuart, Ryan, Mark. Got a good crowd. Okay, a little bit more theory, and then we'll have some fun and do some problems. Okay, I talked to you about work, and I gave you a couple of formulas there. You might not be used to that one. Now, the next topic on our theory is the work energy theorem. I don't know if your book calls it that. I think your book calls it, let me see what they call it. Just a minute here, I'll find it. They call it the principle of work and energy. Most books call it work energy theorem, but this book calls it the principle of work and energy. And the way I like to write it is like this. This is the total work done on a body, the sum of all the work done on a body, and this is the change in kinetic energy of the body. Now, your book writes it differently on page 480. They write it like this. I guess to confuse you, I don't know. That doesn't look at all like that, and that doesn't make a lick of sense. But see, their symbol for work is a U, and their symbol for kinetic energy is a T. So this would be T1, this would be T2. Now, if you put that T1 over here, you'd have T2 minus T1. Well, that'd be the change in kinetic energy, and this is the sum of all the work done. It's the same thing. It's just written in their secret notation there, but we're not confused. If you are, just speak up. Now, I think I proved this work energy theorem to you long ago, and I'm not going to prove it to you again. Read the book. But it's the second most important equation in the course. It's extremely powerful. The only equation that's more important is Newton's second law. But we do need to talk about this business of kinetic energy because you know, I've left these results up there long enough, and you know, this is on Blackboard. You guys can read that for yourself. I'm going to erase all that stuff unless you have a question about it. And I'm going to erase it. That's how you guys did on your test. There were 3 A's. What is that? 6 B's, 5 C's, 2 D's, and an F. Please don't get discouraged if you didn't do well on this. don't get discouraged. You can do this stuff. Maybe it just hasn't clicked yet. Kind of like learning to ride a bicycle, maybe. Some people get right on and ride. Some people fall down and scrape their elbow a few times. The trick is to get back on. Well, I'm going to erase all this and we're going to talk about kinetic energy. Now, you know about translational kinetic energy. Here we'll put a little translational there. That's 1/2 mv squared. We all know that. But see, the rotational, it goes like this. The rotational is 1/2 I omega squared. See, that's linear velocity, but that is angular velocity. And that's mass, and that is your moment of inertia. These are both measures of inertia. Inertia it's a resistance to getting something going. It's kind of like you have inertia in the morning when the alarm clock goes off. And you have to sort of get ready to maybe pile out of bed. Sometimes you don't. That's inertia. But there's two kinds. See, there's translational inertia. Mass is the resistance to trying to get something to move translationally or in a line, going straight. The moment of inertia is also called rotational inertia. And it's the resistance against trying to get something to rotate. Things don't want to rotate. They have inertia, and some things are harder to rotate than others. Now, I think I might have derived this equation here for you, but let me do it again for you real quick. If you had a odd-shaped body, I don't know, something like that, kind of like a potato, and suppose you had somewhere in here is a center of mass. A lot of times they call it G. It's center of gravity, okay? G for, or they could say CG, center of gravity. Now, if you just had a little chunk of mass over here someplace, we'll call that dm. And there'll be a distance to that of r. Now, if this thing's rotating, and if it's in pure rotation, there it's rotating with an angular velocity omega. We're showing you how to get this equation right here. Well, then the little teeny tiny bit of kinetic energy caused by that one little chunk of mass would be 1/2 times that little chunk of mass there, that little particle of mass, times the velocity squared. Well, see, the velocity of this particle, if it's rotating about the center of gravity, then it's that velocity is equal to r omega. So you go r omega, but you have to square it because it's 1/2 mass times velocity squared. There you go. Now, if you wanted the total kinetic energy of the entire potato, or whatever that thing is, It will put a little total down underneath there. Then you'd have to add all these up. That's what integration does. It adds up a bunch of stuff. Okay, you all took calculus, you know you can pull out the constants. 1/2's a constant, you can pull it out. The mass, well, no, that stays in because we're going to do all the little pieces of mass. But now r is not a constant, it varies. But you know what? Omega squared is a constant. Omega is a constant. Every particle in this potato has the same omega. If I spin around, if I turn around 180 degrees, my nose turns 180 degrees as long as I don't swivel my head. My elbows turn 180 degrees as long as I don't move my arms. Every part of me rotates. If I rotate, well, I was thinking 360 degrees. Yeah. If I rotate 360 degrees, complete circle, every part of me rotates 360 degrees. Every part of this potato has the same omega, so you can pull it out, and here's what's left. What's left is an r squared dm. So the total kinetic energy, the total kinetic energy is 1/2 omega squared times this thing. Well, this is the definition of your moment of inertia. It's equal, by definition, it's equal to r squared dm. There you have it. So here we go. Here's our total kinetic energy. It's equal to 1/2 I omega squared. That's where that formula came from. That makes sense? I'm hoping it does. Now here's the tricky part. What if this potato is not only rotating, but it's translating? Suppose the potato has a velocity about, I don't know, heading that way maybe. We'll put like VG there. The potato has a velocity about some point. Well, where are we going to put that point? I don't know. It could be inside the potato or it could be outside the potato. Let's put it right here. Let's say you have some point here that at that instant, that could be your ICZV. There you go, right there. At that instant, every point in the potato is rotating about that point. It's not rotating about the center, it's rotating about that point. And see, that means that this velocity here of the center of mass is equal to this value here, call that RG maybe. It's a nice name for it. RG times omega. Now the omega is the same omega of the potato because this is strictly a translational velocity, and every point on the potato has the same angular velocity. So here's what you have to do to get the total. If you want the total kinetic energy of a potato, or anybody that's rotating about its ICZV, you have to add to it that translational kinetic energy, which is it's like that. See, that's the velocity, and when you square it, you get RG omega, and then you square it. Okay, great. See, this is the rotational, and this is the translational. In general, the the total kinetic energy is equal to the kinetic energy of translation plus rotation. See, here they are. Here's the two kinetic energies. And if you add them together, guess what? You get the total. That makes sense? Now let me show you a wonderful equation here. You can do a little bit of algebra with this. Let's see if I can do that. Look at here. I can factor out 1/2 omega squared. And what I'll have is I'll have an I plus mRg squared. Did I do that right, math students? And I think I did. I think I did. Okay. You know, this looks kind of familiar. It kind of looks like the parallel axis theorem, doesn't it? Kind of looks like the parallel axis theorem. Well, so what? Well, see, that's, I forgot to put the little IG in there. There we go. Yeah. This here is the moment of inertia about this, call it point O maybe, the ICZV. And so the total kinetic energy is equal to 1/2 I sub O omega squared. Wow. Yeah. If you have a fixed pivot, this has got to either be a fixed pivot or a ICZV, which stands for instantaneous center of zero velocity. So we have just come up with a wonderful equation for the total kinetic energy. Well, that's enough theory. Now we're going to work problems. Do you have any questions? Well, let me review briefly what we just learned, or hopefully learned. I need the room. I'm going to say goodbye to all this. It's all in your book, by the way. You could read the book. What we have just learned is the kinetic energy, the total kinetic energy of a body is equal to the kinetic energy of translation plus the kinetic energy of rotation. And and that's equal to 1/2 I of CZ, how do they say it? ICZV, there you go, times omega squared. See, this is 1/2 mv squared. This is 1/2 I of g omega squared. And this is 1/2. If it's a fixed pivot, we call it I sub 0, that'll work. So there you have it for the total kinetic energy. Okay, now we're ready to work problems. Here we go. Any comments or questions? All right, well, let's work problem 1811 to start with. We're going to do problem 1811, and we've got some theory now. I'll get rid of all that stuff there, and let's see. Let's see what this 1811 is. This is on page 490. Let me find it here. Okay. I'm looking at 1811. There it is. All right. We have a kind of a disc type affair here. A wheel. We'll just call it a wheel. There's your wheel. And the radius of gyration is 0.3. It's a 20 kilogram wheel. Now the radius is 0.4. The radius is 0.4 meters. But the radius of gyration is 0.3 meters, just 0.3 meters. Okay. So what? Well, you can get the moment of inertia of the wheel by going m times the radius of gyration squared. That's a nice little formula. This thing here is called the radius of gyration. Do I need to show you where that is in the book and explain it? I've done it before, but I'll be glad to do it again. Somebody just has to ask me, did I spell gyration right? I don't think that's right. Right. Let me see if I spelled that right. G-Y-R-A-G, yeah, I did that right. Yeah, see there? Even a blind squirrel finds a nut now and then. Okay, well, let's figure out what it is. If this is 20 kilograms, that's 0.3 meters, and we square it. I can almost do that in my head. Come out to be 18. Is it 18? Let me see. 20 times 0.3 squared. No, it's 1.8. A kilogram meter squared. That's the moment of inertia about the center of mass or center of gravity. Did I do that right? Yeah, we're doing great. Okay, and now they've got a rope here, and somebody's pulling on it with a force of 20 newtons. So let me put that in. I like my forces in red. So we're going to put 20 newtons there. Now there's going to have to be a force here. I have a gut feeling it's going to have to be 20 newtons because that thing's not going anyplace. Some of the forces on that wheel translationally should be 0. So that's 20 newtons, but we don't really care about that right now. They want us to find something else. They want to know the angular velocity when it's gone 4 revolutions. Okay. We're going to use this equation here. It goes like this. Now let me ask one of my, I want to see if anybody's awake out there. Taylor, let me pick on you. You showed up early this morning, but you told me that you might be in a different part of your warehouse there. Are you with me right now, Taylor? Nope. He told me he was working in this place. and he's probably having to do something else. Let's go to somebody else. Let's go to my friend Stuart. Stuart, unmute and say hello, please, Stuart.
Hello.
Yeah, hey, Stuart. This equation is the second most important equation in our whole course, and it has a name. What's the name of it? This equation right here. Got a
Is
name.
it the work energy theorem?
That's it. He's got it. Stuart got it. Good going, Stuart. Well, that's what we're going to use. Well, see, there's a force right here. I think it's 20 newtons, but we don't really care what it is because it's not moving. It's just holding that wheel from falling. It doesn't do any work, but this one does. And the amount of work it does will be the force, which is 20 newtons, times the distance you move it. Now, they said we do 2 revolutions. No, 4 revolutions. Well, see, 4 revolutions, the distance that you're going to move this will be 4 times the circumference. The circumference of a circle is 2 pi r, right? Yeah. So you go 4 times 2 pi r, which is 0.4. And I think you're moving this, I think that force moves it. Let me do that on my calculator. 4 times 2 times pi times 0.4. I'm getting 10.05, blah, 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 meters that you move it. So see, if you multiply the 20 newtons by the 10.05 meters, you'll get your joules. And that's going to equal to the 1/2 I omega squared. Well, the I is 1.8, and there's your omega squared. So put that in your calculators. There's an equation. I'm going to shut up for a minute, and then I'm going to call on one of my wonderful students, and we're going to get the, I think that's what they wanted. Read it. It says, yeah, angular velocity. We're going to find it. You find it. Go for it. Okay, I'm going to call on somebody. Let's see here. Let me find somebody here. Shane, unmute and say hi, please.
Morning.
Shane, have you figured out this omega here, this angular velocity of that wheel?
Yeah, I got 14.9465.
That's what I got. That's exactly what I got. I got 14. We'll just round it off to 9.5. Hey, Shane, what's the units on that?
Radians per second squared.
You're right. It's just radians per second.
Oh.
Yeah. It's not squared. It's just radians per second. And since radians don't have any dimensions, I just went seconds to the -1. Okay. Now let's see how we did. This was problem 1811. And I'm going to look in the back here and see what the answer book says here. 1811. Answer book says 14.9 radians per second. The book says 14, they're just too lazy to put anything else on there. And they said radians per second, which is fine. So, hey, we did great. We conquered that. Shane was absolutely right. Any questions? We're going to do another problem now. Any questions? Okay, well, let's do a different problem. Here we go. That was fun. This one is 1814. In 1814, I took a little trip along with Colonel Jackson on down the Mississippi. We took along some bacon and we took along some beans. Oh, gee, I forget the rest of the next line there. But I do know that we fired our guns and the British kept a coming. Fired our guns and the British kept a coming. There wasn't as many as there was a while ago. You guys have probably never heard that song. But this is 1814 that we're doing now. And it's on page 491. I'm just curious, has anybody ever heard that song? If so, unmute and say so.
I have.
Who am I talking to?
This is Stuart.
Stuart. Yeah, Stuart's heard that. Do you know what that song was all about? It's a historical thing, Stuart. What was it? It was the War of. Do you remember what it was? Stuart doesn't remember. Anybody remember what war that was that that song is about? Nobody.
1812.
That's it.
Sorry.
That's it. 1812. I think that's the war that they burned the White House down. They burned the White House down. 1812. Yeah. But right now we're looking at 1814, and I found it here. Okay. Well, let me draw you the picture here. There's a rod here, and it's got a pivot there. It's three meters long. But now wait a minute, they have a force there. I like my forces in red. Let me put that force in red down here. Okay, how big is it? Let me read it here. 150 newtons. 150 newtons. There's a force there. I get the feeling this thing's going to start spinning, don't you? Now let me keep reading now. It's a 10 kilogram uniform slender rod. Okay, so it's 10 kilogram. Yeah. Determine the angular velocity of the rod when it's rotated 180 degrees clockwise. Well, you guys, when it does that, it goes zinging around here, and the rod's going to be way up here someplace. 180 degrees, yeah. And now there could be forces acting here at that pin, but those forces don't do any work. But we need to put the gravity on here. You know what? There's a gravitational force right here of 10 times 9.81. You know what? There's a 98.1 Newton gravitational force acting the whole time. Now, it's going to move it from here up to here as it rotates. And now what we're going to do is we're going to use this formula here. It's the second most important formula in our course. And I think that's what they want. They want the kinetic energy, right? Let me read it. Let's see. Yeah. No. They want the angular velocity. They want us to find the angular velocity when it gets up here. See, it's rotating, it's spinning, and it's spinning so many radians per second, and that's what they want. Okay. Well, during the whole trip, even when it's here, when it's down here, you're still going to have the 150, only the 150 is going to be doing that now. You understand? It said the 150 newtons is always perpendicular. Read it. The force is always perpendicular. That's right. So that thing is it's going to do some work. Now, how much work? Well, it'll be 150 newtons times the total distance. Now, if you go halfway around a circle, it's not 2 pi r, it's just pi r. So it's pi, probably should put my units in there. It's pi r, and r is 3 meters. So I think that's the total work done by that. But see, there's another force here. That 98.1, that's gravity. And gravity is doing negative work because it's not going down, it's going up. Do you understand? When a force is going down, but the body is going up, that's negative work. So you're going to have to subtract the work that gravity does, which is 98.1 newtons, times this distance here. Well, that distance there turns out to be 3 meters. Because that's 1.5 meters, and that's 1.5 meters. So you got the 2 work terms. And then on the right, since you've got a fixed pivot, you can use this here. You can go 1/2 I sub O omega squared, where this is O, okay, the fixed pivot. Well, we just need to find what I sub O is. Well, there's 2 ways. One way is you can take I sub G and you can add to it using the parallel axis theorem, and you can get it that way. And that will be, well, you have to look this up. I think it's 1/12 ml squared. So let's do it that way. If you do it that way, you get 1/12 10 kilograms times 3 meters squared plus 10 kilograms times the distance between O and G. See, there's G. That's 1.5 meters squared. All right. Somebody do that and tell me what I sub O is. I'll shut up for a minute, and I want you to find I sub O, the moment of inertia about the fixed pivot. Go for it. Well, let me go to one of my wonderful students. Let's go to my friend, Ryan. Ryan, unmute and say hello to me, Ryan, please.
Hello.
Hey, Ryan, what'd you get for this moment of inertia about that fixed pivot? What'd you get?
I got 30.
That's what I got. I got 30. What's the units on that, Ryan?
Um, is it meters to the fourth? Hang on.
No.
I'm not sure.
Well, look at here, Ryan. You got a kilogram and you have some meters squared. What do you think that's going to give you?
Is that newtons?
No, it's not. It's close. It's kind of close to a Newton, but it's a kilogram, and that's a meter squared. When you multiply them, what do you get, Ryan?
I'm not sure. I don't remember.
That's okay. Have you ever noticed when somebody asks you something, you can't remember what it is? You know this. You know this darn well. It's just a kilogram meter squared. That's all. Just a kilogram times a meter squared. You knew that, didn't you, Ryan?
Yes.
Yes, you knew that. Now let me show you there's another way to do this. There's a quick and dirty formula in the very back of your book. It's where my thumb is wiggling. It's in the back flap of your book, and it says 1/3 ml squared. Now what this is the moment of inertia about the end, not the middle. See, the 1/12 is the formula for about the center, but if you do it about the end, there's a quick and dirty formula. You don't have to use the parallel axis theorem. And here's what you'll get. Put that in your calculators and tell me what you got. I can do that in my head. I picked on Ryan, and Ryan was a good sport. Let's go to my friend Mark. Mark, unmute and say hello for me, please, Mark.
Hello.
Yeah, what do you get when you use this formula, Mark?
30.
You get 30, you betcha. You understand that's just a quick and easy way to get the moment of inertia about a slender rod if you're rotating about the end. See, we're rotating it about the end. And the formula is 1/3 ml squared. Okay, well, let's finish our problem here. Look at here. Here's an equation. And we know what this is. We did it two different ways. Here's an equation. Here, I'll box it up for you. We know what that I sub O is. It's 30. So put in that 30 and solve for omega. I'll shut up and then I'll ask somebody. Find omega is what we're doing right now. We have an equation. There's only one unknown. We know what this I sub O is. It's 30. So find omega. I'll be quiet and give you a minute to do it. Right now, if somebody just tuned in, we're doing problem 1814. It's on page 491. We're trying to find omega. It's a Greek lowercase. It's the last letter in the Greek alphabet. We're trying to find omega, the angular velocity. Well, let me ask somebody here. We're going to go to my friend, oops. We're going to go to my friend, Ashley. Ashley, unmute and say hello, please.
Hello.
Hello. Hey, Ashley, did you get this omega?
I got 8.6387.
That's what I got. I got 8.63. You could round it off to 9. Ashley, what are the units on that omega?
Radians per second.
Good going. Since radians are dimensionless, I'll just go 1/seconds. Now let's see how we did. This was 1814. And I'm going to look it up in the book here. And we'll see what they said. They said 8.64. You know what the book says? 8.64 radians per second. Yay, we did good. They just rounded off. Is there any question on that one? Okay, well, let's do some more. Let's do some more. I'm going to erase all this stuff because we can do that, can't we? Anybody want to say something? Now's the time because I'm going to erase this. Okay, we're going to erase all that. And we're going to do another one. Here we go. Now this one here that I want to do is F188. It stands for fundamental problem. I really like these because they even show you how to do them in the back. That's nice of them. Now this one's at a 30-degree angle. 30-degree, huh? Okay, well, it's about like that, maybe. 30-degree angle. And there's a spool. You know what it is? It's a spool. And this is F188. Let me find it. I got lost. There it is. It's on page 502. Now they have an interaxial. They have it's a spool. And spools have an inside axle like that. And the radius on that is 0.2 meters. 0.2 meters. And then the radius going on the outside of the spool is 0.4 meters. Let me write that a different place here. Let's see. This is 0.2 meters. Yeah. And And then this is 0.4 meters. There we go. Yeah. And then they have a kind of a line here, a cable maybe, or a rope, a cord. There we go. Now let me read this. A 50-kilogram reel. Well, let me write that down someplace. 50 kilograms. Has a radius of gyration of 300 millimeters. Okay, well, let's get the moment of inertia about the center of gravity. See, this is G right here. I should have made this bigger. Made it too small. It's too small. I should have made it bigger. Oh, well. This is going to be the mass, 50 kilograms, times the radius of gyration, which is, well, it's 0.3 meters squared. Okay, well, let's see what that is. Could almost do that in my head. Is it 0.45? Is that right? If I did it in my head, probably not. Let me see. 50 times 0.3 squared is, no, it's 4.5. Kilogram meter squared. Now, what's kind of weird about this one is it's slipping. It's going down the hill and it's rotating, but it's not, this is not the ICZV, because there's motion, there's relative motion between the wheel and this surface of that hill. It says it's a smooth inclined plane. So that means there's no friction. So just put some oil or grease there on that hill. It's spinning, but it's so slick that there's no friction. But here's the secret to this problem. This thing has an ICZV, call it point A. That's the ICZV. It's actually rotating at that instant about point A. Does that make sense to anybody? It's an awfully small diagram. Okay, so what we need is the moment of inertia about point A. Well, you know, the equation goes like this. Now, this equation has a name, and you all know it. I could ask any one of you, and you could tell me what the name of that equation is. We know that equation. Any one of you knows that. Here, let me ask somebody. Braxton, unmute and tell the class the name of this equation. Go for it, Braxton.
That is the parallel axis theorem.
Boy, Jiv. Braxton knows what it is. Are there two L's in parallel? I think there are. That's called the parallel axis theorem. Okay. Well, I'm going to shut up for one tiny minute, and I want you to find that. We found this one. It's 4.5. What's this one? Go for it. Well, I've got an answer. Hey, Braxton, since I was just picking on you, what'd you get for this moment of inertia about point A?
6.5.
That's what I got. And Braxton, what are the units for moment of inertia?
Kilogram meter squared.
You, by Jove, you got it. So we're doing great. Now let me go back and see what they want us to do here. Just a minute. Let me read this. It says here it's released from rest. Find the angular velocity when the center O has traveled 6 meters down the smooth inclined plane. Do you understand this thing's going to go? It's going to go 6 meters, and it's not going to be here anymore. It's here. I'll draw you kind of a ghost. It's really a spool, isn't it? The artist's rendition of the spool. Not very good drawing there, but you get the picture. It's going down the hill. And what do they want to know again? Let me read it. Angular. They want to know the angular velocity. See, it's spinning. It's got an angular velocity when it gets down there. And here's how we do it. We take the sum of all the work done on the body, and that's going to equal the, since it has an ICZV, we can use this lovely equation that I derived for you earlier today. Ta-da, there it is. We got the IA, it's the 6.5. Not the F, that's wrong. There we go. If we can only figure out the total work done on this body, we can do this. Okay, well, to do that, you need to get all the red stuff on here. Okay, well now, acting on the wheel, we have gravity. How much is that? Well, what's 50 times 9.81? Just a minute. 50, 9.81. I get 490.5. I have 490.5 newtons. That's gravity. And then you have a normal force acting on it. And then you have this rope. I think this rope is going to be pulling. There's going to be a tension in the rope. Call it T. They said there's no friction, so we don't need to worry about friction. They said it's a slick, smooth surface. You know what? I think those are the only 3 forces acting on it. The thing about this tension force is it doesn't do any work. Well, it certainly doesn't move up here. That's connected to this, I don't know, tied up to something on the wall there. It doesn't move there. And it's kind of like when you have something that's rolling, there's no relative motion between your point A on your spool and your point A on this rope. It's kind of like rolling. It's not rolling, it's unwinding, but unwinding is like rolling. There's no work. To do work, you've got to have relative motion between this cord here and the spool. There isn't any. It's the instantaneous center of 0 velocity. There is no motion between the spool and that rope at point A at that instant. The normal force also doesn't give you any work because it doesn't move. But the 490.5 does. That's the only force that does any work. and we can figure out how much it is, maybe. How far did it go? It says here, it goes 6 meters down the smooth inclined plane. Well, if it goes 6 meters, then it drops 3 meters. This is a, no, that's not right. No. Yes, it is right. Look, if you have a 30, 60, 90 triangle, we all know and love 30, 60, 90 triangles. If this goes 6 meters, did you know the small side of a 30, 60, 90 triangle is 1/2 the long side? Did they teach you that in school? If you have a 30, 60, 90 triangle, the small side is exactly 1/2 the long side. I hope they taught you that in school. See, the 30 degrees is here. The sine of 30 degrees is the opposite over the hypotenuse. How's that go, SOHCAHTOA? S-O-H. Isn't that right? Sine is the opposite over the hypotenuse, SOHCAHTOA. Well, the opposite side's 3 and the hypotenuse is 6. 3 over 6 is 1/2. You guys knew that. You knew that the sine of 30 degrees is 1/2. If you don't believe me, put it in your calculator. Put in sine of 30 and push the button, and it says 0.5. Well, boy, Jeff. So see, the work done by gravity is going to be 490.5 newtons times 3 meters equals a 1/2, 6.5 omega squared. Now I'm going to shut up for a minute. I want you to find the omega of that spool. Go for it. Okay, let me go find somebody here. Let's see, I've already picked on a lot of people this morning. Shane, I don't know if I've picked on you yet. Shane, unmute and say hello, please, Shane.
Hey.
There you go. Shane, what'd you get for this omega, Shane?
21.278
That's
grams per second.
exactly what I got. 21 point, I don't know, we'll round it off to 2.8 maybe radians per second. Now let's see how we did. We're gonna look and see how we did. Here we go. Go to the back and look up F18.8. F18.8. Back in the back, it says F18. F18.8. Says here 21.3 radians per second. The book says 21.3 radians per second. We got 21.28. They just rounded off. We'll forgive them for that. Hey, we conquered that one. Well, let's do another one. We got time for one more, maybe. This one is on page 320. 326 maybe? No, that can't be right. No, it's page 493. Turn to page 493. We're going to do one last problem together here. This is problem 1821, but I'll answer any question if anybody has it. Any comments or questions on F18.8 before we tackle 1821? Well, okay, say goodbye to fundamental problem 18.8. Now this is problem 1821. I'll try to draw it a little bigger. That last one was too small. Now, this is a yo-yo. We're talking about a yo-yo. I wonder if any of you have ever played with a yo-yo. Probably what I should ask is, I wonder if any of you have never played with a yo-yo. My guess is just about everybody's played with a yo-yo. If you have never played with the yo-yo, unmute and speak up. Go for it. If you've never, ever played with a yo-yo, unmute and speak up. Because there's something wrong with you. If you've never played with a yo-yo, you're missing out on part of life. Okay, go ahead, speak up. Who's out there that's never played with a yo-yo? Oh, see? There isn't anybody. We've all played with yo-yos. Okay, great. Well, let's do this yo-yo now. This is 1821. And here I'll try to draw it. You have this inner spindle, I guess you could call it. On an actual yo-yo, it's smaller than that. I think I drew my spindle a little bit too small. And here's your string, and then here's the person's little artwork there. They've got their hand there. Now a yo-yo has a weight of 0.3 pounds. Oh, we get to use Inglés, senor. That's good. We got to know how to work in English. You know what? We got 0.3 pounds. The radius of gyration is 0.06. Let me write that down. Radius of gyration is 0.06 feet. Okay. Now our first job is going to be to find the moment of inertia about G. There's G right there. And I'm going to shut up for a tiny minute. And I want you to find the moment of inertia of our yo-yo. You know the equation, it's m times the radius of gyration squared. And we've got everything. We got the mass. Well, kind of. All right, I'll be quiet. You find the moment of inertia, and I'm going to do it, and we'll see if we can agree on this. Go for it. Well, that's not giving you enough time. Let me try Taylor again. Taylor, are you where you can answer us this time, Taylor? Nope, he can't do it. That's all right. He's working. Stuart, let me pick on my friend Stuart. Hey, Stuart, unmute and say hello, Stuart.
Hello.
Stuart, what'd you get for the moment of inertia about the center of gravity for this yo-yo?
I got, let's see, 3.35 times 10 to the negative 5.
That's what I got. How about that? 3.35 something times 10 to the negative. Stuart, what's the units on that? Got to have units.
Is it pound feet squared?
No. Try again. You got the right answer. You must know what you're doing, but it's not pound feet squared. See, I'm glad we're doing this because Stuart's learning something. He's learning that mass, that's mass. Mass is in slugs and force is in pounds. He probably already knew that, but sometimes we need to hammer this in so that it sticks. This is slug feet squared. Are you okay now, Stuart?
Yes.
Anybody else need help on that? Okay, well, we're off and running. Now, what are we supposed to do? Let me read this. It says here, how far must it descend in order to have an angular velocity of 70? Okay. Now they gave us this radius here. That radius is 0.02 feet. The radius of the inner spindle is 0.02 feet. And this thing is going to go down. It's going to spin. And when it gets down here someplace, I'll try to draw kind of a ghost yo-yo down here. There's your ghost yo-yo. It's supposed to be spinning 70 radians per second. That's pretty fast. Holy cow, 70 radians per second. Gee whiz. That's clipping right along there. And what do they want to know? How far? Yeah, they want to know how far down it has to go. See, what they want to know is how far down, I don't know, call it H maybe, and the height that it descends there. But we better get with it. We're running out of time here. Well, how do you do a problem like this? Well, you use this equation here that goes like this. And this equation has a name. And we've mentioned it a bunch of times. It's the second most important equation in our whole course. And it's called the work-energy theorem. Only your chapter calls it the principle of work and energy. Okay, well, now to find this total work done, what you do is you get your red pencil out and you put your gravity, the gravitational force is 0.3 pounds. See, force is in pounds. They said it's a 0.3 pound yo-yo, so that's your gravity. Now this rope here has tension in it. Now, it would be fun to find what that tension is if we only had time, but I don't think we do. We're running out of time. But those are the only two forces acting on the yo-yo that I know about. And the thing is, the tension doesn't do any work because it's unwinding. It's like rolling. See, there's no motion, relative motion between the spindle and the cord there. It's like rolling. Rolling, it doesn't give you any work. The only work that you get is the 0.3 pounds times the height that it travels, the h. Okay. Now what we're going to need, oh gee, I'm running out of time. What we're going to need is the moment of inertia about this point A. Let's call it A. That's a nice name for it. And what it is Ig plus the mass times the distance between G and A squared. Parallel axis theorem. Well, let's go ahead and get that. We don't have time to delay. Let's see. I'm going to do that now. Well, hopefully I did that right. And what I got was 3 point blah, 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 blah. And so here's your total work done. And your total kinetic energy will be 1/2 times this here. Okay, they gave us that. They said it's 70, didn't they? Well, plug that into your calculator and solve for h. You go ahead and solve that. I'll look up the answer and we'll see if we get the same thing. This is 1821. And the answer book says that the h is 0.304 feet. Is that what you get when you do that? Let me try it. Boy, Juve, I get a 0.3043 feet, and the answer book rounded it off to 0.304 feet. So we did great. We just did a problem with a yo-yo. Are there any last comments or questions? Because I'm gonna sign off and wish you all well until Wednesday at 9:30, I guess, right? Yeah. Okay. Here's your last chance to say anything. Speak up. Nobody said anything. Bye-bye, students.
Bye.
Bye-bye. Be good.